Hello, this is Unlock Circuits 18EC42 Module 3 Lecture 1. We are talking today about the Part 3. So in the Part 1 we had spoken about the feedback amplifiers and in particular about introduction, the general feedback structure and some properties of negative feedback. In the Part 2 of the lecture series we had spoken about four basic feedback topologies, and Part 3 we are speaking about the series shunt feedback amplifier only. So initially what we said was all the electronic circuits have some sort of negative feedback or positive feedback depending upon whether it's an amplifier or oscillator. Negative feedback has a lot of advantages such as desensitizing the gain, reducing nonlinear distortion, reducing the effect of noise, controlling the input and output impedance, and increasing the bandwidth. So what happens in all these is the improvement of all these is at the cost of the gain. So it's a trade-off between gain and the other desirable properties over here. So we have seen the general architecture of the feedback amplifier, and then we have seen some of the properties such as gain desensitivity, bandwidth extension, noise reduction, and reduction in nonlinear distortion. Further to this, what we spoke about is in the part 2 is the four basic topologies where we discussed about the different types of amplifiers depending upon what the input is and what the output is. So we have a voltage amplifier, input and output both voltage, and that refers to the feedback topology, which is voltage sampling and series mixing, which is also known as series shunt topology. Similarly, we have another one of the amplifier, which is the current amplifier, where the input and the output both are currents. And as well, we see that that corresponds to the basic feedback topology of current sampling and shunt mixing, which is shunt series topology. Then we have the transconductance amplifier, where the output is the current and the input is the voltage, and that straight away corresponds to the current sampling and shunt mixing current sampling and series mixing, which is series topology. The fourth and the last one, we have the trans resistance amplifier, where the output is voltage and the input is current, and that corresponds to the voltage sampling and shunt mixing, which is also known as shunt topology. So these are the four things which we spoke about, and in detail we have gone through that, and now we will take each one of them in much more detail. So now coming to the part 3, we are in now the series shunt feedback topology, and this will straight away correspond to the voltage amplifier. So now we have here a voltage amplifier, which is series shunt topology. That is, at the input side we are doing the series mixing. At the output side we are taking the sampling of the output voltage, which is corresponding to the shunt. So that means output is taken out over here, and part of it, that is whatever output is there, that is multiplied by the feedback network, and we get VF. So that is VF is equal to beta V naught, and that is subtracted here from the VS signal to get the input over here, and that becomes the basic series shunt feedback topology. So we have two situations here. One is the ideal situation and another is the practical situation. In the ideal situation of the series shunt topology feedback amplifier, in that we see that this is the the amplifier is replaced by this model, and the feedback network is replaced by this model. Amplifier is replaced by this model, wherein we have the input resistance, the output resistance, and the amplified value of the input at the output side. And then we have a feedback network where we have V naught, and the VF is equal to beta V naught. So the amplifier and the feedback amplifier, the feedback network, both are considered unilateral. That means the flow of the current is current or voltage or power on the whole is from the input side to the output side and not vice versa. And similarly, in the feedback network, it is the other way around, that is from the output to the input, and it doesn't affect the loading of the amplifier over here. So that is the assumption we'll try to make over here, and then we'll go forward to analyze this particular circuit over here. So the equivalent circuit of the amplifier, the overall, the amplifier with the feedback arrangement is written over here, and that is Vs with RIF, ROF, the input feedback resistance, and the output feedback resistance, and then the AF into Vs all throughout. So what is the value of RIF, what is the value of ROF, and what is the value of AF in terms of the circuit which we have written here? That is what we need to find. So the closed loop gain here just gives us that AF is equal to V0 by Vs. Closed loop gain AF is equal to V0 by Vs. So the value of the output over here is equal to the voltage. This V0 is this voltage plus this voltage. Assuming that ROF is equal to 0, V0 will be equal to AF into Vs, and that will give us AF is equal to V0 by Vs, and that will turn out to be A by 1 plus A beta. This is the standard thing. That is because we need to substitute. In the earlier figure, you can just see here, we need to write in place of Vs, we have the Vi plus Vi minus Vf as the voltage, and then we need to simplify Vf is equal to beta V0. We try to write there, and then take the common factors and try to cancel the V0, and hence we will get the value A divided by 1 plus A beta. So Vs will be equal to Vi minus Vf. Vf will be equal to beta V0, and Vi itself will be equal to V0 by A, and then if you take out the value, Vi is equal to V0 by A. So V0, if we take out there, then निकालो क्या है उस पे बंद करो क्या रीस्टार्ट कर, तुम बैठो, चुप बैठो. So we are going to get over here V0 by Vs just means Vs is equal to Vi minus Vf, and Vi is nothing but V0 by A, and Vf is nothing but the value beta V0 with a minus sign, and then the what you call V0 by A can be taken out, and that leaves us 1 plus A beta as the common value between the what you call two things in the denominator. And V0 will cancel, and A will go to the numerator, and hence we'll get A by 1 plus A beta. Then we need to find the input resistance of the amplifier. The input resistance of the amplifier RIF over here is equal to Vs divided by the value of II. So Vs divided by the current which is flowing here is II, and Vs divided by II will give us the input resistance with feedback. And this II, if we go back to the earlier circuit, over here, the value of II will be equal to, you can definitely say, Vi by Ri. So we are replacing the II as Vi by Ri, and that gives us Ri into Vs by Vi. The value of again Vs is equal to, if you just see over here, is equal to the sum of the Vi and Vf, Vi plus Vf, and that Vi plus Vf can be written here, and Vf is nothing but beta V0, and we will get here beta V naught, and denominator will remain Vi. Vi can be taken out common, and then this will become, once we take out the Vi common, this will become 1 plus beta V naught by Vi. V naught by Vi is A, and denominator will be Vi. Vi cancels, and we are left with 1 plus A beta. So the series mixing increases the input resistance by 1 plus A beta. That is what it shows over here. This Ra is getting multiplied by 1 plus A beta. So the general form for this is, if we have written here resistance, and we can generalize it to the impedance which is dependent upon the frequency over here. S is nothing but j omega. S is a Laplacian, which will give us, as we can substitute j omega in place of this as a function of S. We have written here the input impedance with feedback, and that is equal to the value of Zi. This should have been just Zi, not F. F should not be there. This is the what you call input impedance without feedback multiplied by 1 plus As beta S. So having finished with the input impedance, what will be the output resistance we need to consider? For this, we put the value of the input voltage, signal voltage to more particularly, to be equal to 0. If we make the signal voltage equal to 0 over here, if you make the signal voltage 0 over here, then this is a short, and we are left with only this particular circuit with whatever is the arrangement shown there. So we have here, the RIF rather in the what you call circuit over here, the what you call in this circuit over here, because Vs is equal to Vs is equal to 0, then the output side will have this, and that side will be A into Vi into R0, and we are trying to put a source of Vt, the test source here as Vt. This test source divided by the current I is going to give us the ROF value. ROF value is the resistance looking in this direction, Vt divided by I. Now this value of I is what we need to find out from here, and I is definitely the current through this, and the total voltage in the loop is Vt minus AVI, and that voltage should be divided by R0 to get the value of I, and that is what is written here, Vt minus AVI by R0. Also, the value of Vi, if you see in this circuit, is nothing but Vs is equal to Vi plus Vf, or Vi is equal to Vs minus Vi minus Vi is equal to Vs minus Vf. So if Vs is made 0, Vi will be itself equal to minus value of the Vf. So that is what is mentioned over here. Vi is equal to minus Vf, and Vf itself is equal to minus beta V naught. Vf is equal to beta V naught, and minus is as it is there, and that is equal to V naught itself is our Vt in this particular case. So Vi is equal to minus beta Vt. Now here the consideration is Vs is equal to 0, which we have chosen over here. Otherwise, we are not going to get this. So having written this Vi is equal to minus beta Vt, you can substitute it over here. So that will get Vt plus A beta Vt. And if you just, you can take out Vt common, you will be left with 1 plus A beta, and then the 1 plus A beta you can take on this side, and R0 you can take on that side, again the other side, and I you can take it on this side, then we'll get Vt by I is equal to R0 divided by 1 plus A beta, and Vt by I is nothing but ROF. Therefore, we have written here ROF is equal to Vt by I is equal to R0 by 1 plus A beta. So thus, the voltage sampling feedback reduces the output resistance by the factor 1 plus A beta. In the general form, we can write it over here as ZOF, the impedance at the output after the feedback, is equal to impedance of the output without feedback divided by 1 plus A beta. So that's the ideal situation. Now coming to the practical situation, in the practical situation what we are trying to do is the source voltage is having a source internal source resistance Rs, and the output device will at the output side will have the load, and this load might be part of the input impedance of the device which is following this feedback amplifier. So whatever is there here, that might have input impedance, and that is the one which loads this particular amplifier. Hence, we will consider here as load impedance. Now, having the load resistance or load impedance over here, then we again need to find out RIF and ROF. RIF and ROF. So, RIF and ROF are input and output resistance respectively of the feedback amplifier, including RS and RL. The actual input and output resistance of the feedback amplifier usually exclude RS and RL, but now we need to include them. So now Rin is equal to the Rin, that is the impedance over here, is equal to RIF minus RS. Whatever RIF is there minus RS. So where is this RIF? RIF is here, that is before RS. Rin is after RS. Therefore, RIF is equal to RS plus Rin. So that is Rin is equal to RIF minus RS. And Rout, which is the impedance looking from here, okay? Rather, I should take something like this. ROF is equal to the parallel combination of RL and Rout. And if you simplify that, then we are going to get it as Rout is equal to 1 divided by 1 by the value of the RL minus 1 by the value of the Rout. Okay, so that is the value which we'll get there. So the circuit in one with feedback network represented by its H parameters, whatever circuit which we have written over here, the same thing is replaced. This is replaced by the equivalent, small signal model, and this is replaced by the H parameter model, and then we can try to write it over there. So this H parameter model is H11, H12 V2, H21 I1, and H22. So the source and the load resistances which are there over here should be lumped with the basic amplifier. In addition, the resistance in the feedback should be also lumped with the basic amplifier. So H parameters, two-port feedback network is drawn there. So here we neglect the value of H21. This is neglected. The forward transmission effect of the feedback amplifier, and thus omit the controlled source H21 I1. So this is negligible, hence we neglect this. So having neglected it, we can just try to write the circuit there as the one wherein the H11 is shifted on this side, H11 is shifted on this side, H21 is neglected, the H22 which is there in parallel with the what you call the current source over here, and that is shifted onto the output side of the basic amplifier. So it's not going to do any harm. H22 is going to come over here, that will come in parallel with this, and effectively we will have the value of the effective resistance over here. So now we can determine the value of the beta. So beta is H12, beta itself is the value H12 over here, and because the VF is equal to beta V0 is the value, and in place of beta we have H12. So beta is equal to H12, is equal to V1 by V2 at the value of the current being equal to 0. The value of the current being equal to 0. So therefore, that is the port 1 open circuited, that will be the input port, input side of the port over here, open circuited. This is opened. What is the value of V1 by V2 when I1 is equal to 0? So V1 just means the voltage which is there here, that is VF, and V2 just means the voltage which is V0 over here. So this the quantity which we come across is the VF value divided by the V0 value over here, with the current I1 being considered equal to 0. So now the amplifier circuit is being mentioned over here with the two resistors at these points and the two resistors coming in parallel here with the basic amplifier over here. And to find R11, where R11 is obtained from the circuit over here, we, in the feedback network, we short this and we try to measure the value of the RI, the R11 from this side. The R11 is to be measured from this side by shorting this. So R11 is nothing but V1 by I1 when the shorting is there at the output. So that means V1 by I1 when shorting is there means current is there, but the voltage V2 is equal to 0. So V2 is equal to 0. Similarly, R22 is the resistance measuring from this side, which will give us R22 will be the value of the output voltage divided by the current through it, V2 divided by I2, and when you consider this feedback network as the one which we consider over here, at the time, the value of R22 is V2 by I2. At the time, the value of V1 is equal to 0. And the gain A is defined as A is equal to V0 dash by Vi dash, and beta is obtained directly from the feedback network by connecting the output voltage over here and the measuring the feedback voltage over here. That will be beta into V0 dash. Vf is equal to beta into V0 dash. So the value of beta will be Vf by V0 dash, corresponding to again the I1 equal to 0. The I1 is the current which is flowing over here. So taking an example of this here, you can see that we are taking an op-amp which has an open loop gain mu and a differential input resistance RID and an output resistance R0. We need to find the expression for A, beta, and the closed loop gain V0 by Vs, the input resistance Rin, and the output resistance Rout with mu. Mu is nothing but A, the amplification of the amplifier, that is equal to 10 to the power 4, RID equal to 100 kilo ohms, and R0 is equal to 1 kilo ohm, RL is equal to 2 kilo ohm, R1 in the feedback network is 1 kilo ohm, R2 is equal to 1 million. So you have here RS, you have the RID, you have the mu V1 here. So mu is nothing but our A, and R0 is there over here, and this is RF, R2 and R1 are here. This is R1 and this is R2. So we have RL and the output will be, this will be ROF and this will be ROut. Similarly, this will be RIN and this will be RIF with feedback. So taking the equivalent circuit there, so we can just say that here, if you try to remove from here and put it, the ground output should be shorted, then definitely these two are going to come into the parallel combination of that. And that parallel combination is going to come here. So that is why we will have here the equivalent circuit on the input side as a VI dash RS R1 in parallel with R2. At the output side, we need to consider the, you can see that we need to consider at the output side the, what you call this and this resistance are going to come in series with each other, R2 and R1, and that will come in parallel with R2. And the same is written there, and we have R0 and mu VI. So we will have here R0 and mu VI RL in parallel with R2 plus R1, summation of the two resistors R2 plus R1. So what is the gain of this amplifier with feedback? So really speaking, this should have been AF. So AF is equal to V0 by V0 dash by Vi dash, V0 dash by Vi dash is what is there. So first we can try to find out the value of, the, we can try to write V0 by Vi dash, and what is V0? We can try to measure in terms of this mu Vi. So the output here, V0 dash is equal to mu V1 multiplied by the parallel combination of this divided by the sum of R0 and the parallel combination of this. So parallel combination of this is RL in parallel with R1, R2, that is what is mentioned over here. Then divided by R0 plus, this R0 is written here, R0 plus the parallel combination of both of that. Okay, that is going to give us the value of mu V1. So this quantity will be there, and we are left with V1 there, and divided by Vi dash. V1 by Vi dash. But what is V1 by Vi dash? V1 by Vi dash we can find out from here. V1 is the voltage here across RID. Vi dash is the voltage across all the three. So V1 by Vi dash, current flowing through this is just the same, is nothing but this resistance divided by the sum of all these resistance. RID divided by RS plus Vi plus R1 in parallel with R2. So V1 by Vi dash will be RID divided by sum of all these three, and that is what is written over here. So thus, if you try to substitute all the values RL, R1, R2, RID, RS, or RID, all those values, you get A is equal to approximately 6000 volts per volts. Then coming to the feedback arrangement over here, the VF value is the voltage across R1, whereas the VO dash is the voltage across R2 plus R1. So beta, which is equal to VF dash by the value of V0 dash, will be equal to R1 divided by R1 plus R2. So if you substitute R1, R2 there, we'll get approximately 10 to the power of minus 3. Because the value of R1 is mentioned here in the formula. R1 is 2 kilo ohms, R1 is 1 kilo ohm, and R2 is 1 mega ohm. So therefore, this will be, you can just neglect the 1 kilo ohm compared to 1 mega ohm, and hence we'll get 1 kilo ohm by 1 mega ohm, that is equal to 10 to the power of minus 3. So the voltage gain AF is equal to A by 1 plus A beta. That is, A 1 plus A beta is the quantity which we need to find, and that will be 1 plus 6000 divided by 1 plus 6000 into 10 to the power of minus 3, and that will be 7, and we will have the value 857. Similarly, the input resistance is RIF is equal to RI into 1 plus A beta. The value of Ri itself is nothing but Rs plus RID plus R1 in parallel with R2. So that will give us 111 kilo ohms, and RIF will be that Ri multiplied by 1 plus A beta. 111 multiplied by 7 will give 779 kilo ohms. The Rin value will be RIF minus Rs if you subtract from the feedback resistance with feedback, which is 777. The value of Rs over there, then you'll get 739 kilo ohms. Then we have the output resistance ROF is equal to R0 by 1 plus A beta, where R0 is R0 in parallel with RL in parallel with R1 plus R2. So if you go back over here, we should short this to measure the Thevenin's equivalent resistance here, and that will be R0 in parallel with RL in parallel with R2 plus R1. And that is what is mentioned over here, and that will give us 667. ROF is 667 by 7, and that is 95.3 ohms. And that will give us ROF is equal to R out in ROF is equal to R out in parallel with RL. So therefore, R out will be, we need to write again the formula, which is corresponding to 1 divided by 1 by the value of ROF minus 1 by RL, and that will get as 100 ohms. Okay, the formula which we have written over here for the out. Okay, 1 divided by the ROF minus 1 by RL. This finishes the lecture on the series shunt feedback amplifier. In the next class, we'll take up the series feedback